friends, now in this video class we are going to discuss about 11th standard computer science chapter 2 number systems. Last class we discussed about binary arithmetic. Now in this class also we are discussing about the continuation of binary arithmetic. Okay, now you can see the examples here. Perform binary addition for the following numbers, that is minus 21 base 10 plus 5 base 10. We already studied now how to represent a negative numbers in binary representation. Yes, how many ways you can able to represent a signed numbers in binary form? There are three different ways. Yes, sign magnitude method, ones complement method, and twos complement method. Okay, you can use any one of the method. You first convert this minus 21 into the binary form. Okay, so when you want to represent negative numbers in binary form, we can use any one of these methods. Okay, in this example we are going to implement the twos complement method. Okay, for changing minus 21 into binary form. Okay, now you can see the steps needed to do this sum. So step 1, change minus 21 and 5 into binary form. Here minus 21 is the negative number. For that, how we can find the twos complement method? First you can find the positive 21 base 10, that is positive decimal number into positive binary number, and then you just find the ones complement of that binary number, positive binary number, and then we add 1 to that ones complement, we get the twos complement of the given number. Okay, you just recall the concept of twos complement method. Can you able to remember how we can find the twos complement? First you can find the positive decimal number binary equivalent value, and then we change that binary bit into 8-bit format. Okay, and then we convert this 8-bit format into ones complement. How we can find the ones complement? We just change zeros into ones and ones into zeros. Now we can get the ones complement numbers. Okay, and then we add plus 1 to this ones complement number, we get the twos complement value. Okay, that concept we all implement here again. Okay, now you can see this table, first table 21 base 10. So we are going to find the binary number. Either we can use sum of powers of 2 method, or we can use a repeated division by 2. Okay, so now in this example we are using sum of powers of 2 method. 21 base 10, the nearest square of the nearest power of this number is 16. Okay, and then write down the remaining powers. So 16, 8, 4, 2, 1, that is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. Okay, so 2 power 4 is 16. So 2 power 5, if you move on next power 2 power 5, 32. The number 32 is greatest to the given number. So no need for 32. We just stop from 2 power 4. Okay, that is 2 power 4 is 16. Okay, now you can find the binary number. We just put 1 in this 16. Okay, now we minus 21 minus 16. What we get? We get the answer 5. Okay, now we can compare the remainder value with the next square. The next square is 8. So next square is greater than the remainder value. If the square is greater than the remainder value, then you can put 0. Okay, if the square is less than or equal to the remainder value, then you can put 1. Okay, now the remainder value is 8 and the power is remainder value is 5 and the power is 8. So 8 is greater than the remainder value, so you just put 0, and then you can see the next power. Next power is 4, so the remainder value is 5. This is less value, so you can put 1 in that place 4. And then next we take this value 5 minus 4, what we get 1. So the remainder value is 1. The next square is 2, so 2 is greater than 1, so you put 0. And then take the next bit is 1 is equal to 1, so you put 1 minus 1 is equal to 0. Now the binary value for positive 21 is 10101. So before going to ones complement, we just change this 5-bit number into the 8-bit format. Okay, for that what you want to do, we just add preceding zeros for this binary numbers. Okay, so 0 0 0 1 0 1 0 1 base 2. So this is the binary value for positive decimal number 21 base 10. Now we are going to calculate the 2's complement of this given number. If you want to calculate 2's complement, you first find the 1's complement and add 1 to that number. Okay, so see the step 2, see second step 21 base 10. What is the positive binary number for this number? 0 0 0 1 0 1 0 1. Now we can find the ones complement. How we can find ones complement? We just change ones into zeros and zeros into ones. Okay, so 1 will be changed into 0, 0 again 1, 1 will be changed into 0. We just see the 21 base 10 binary number and ones complement. Here interchanging the values. Okay, that is all ones are changed into zeros and all zeros are changed into ones. This is the ones complement value for 21 base 10. And then next we are going to find the 2's complement. For that we just add 1 to the least significant bit, that is LSB bit. That is the first bit. Okay, so we add 1, 0 plus 1 1. So remaining numbers all are same. So we just write 1 0 1 0 1 1 1. So this is the 2's complement value for 21 base 10. So this is the binary value for minus 21 base 10. Okay, so now we see in the second step 1 second part, we are going to find the binary value for 5 base 10. So 5 base 10 directly, this is a positive number, so we can find directly. Then value for binary value for 5 base 10 is 101. So we change into 8-bit code. That is, we just add 5 preceding zeros to this number. Okay, 5 zeros 1 0 1 base 2. Now we are finding both the binary value for both the numbers, that is minus 21 base 10 and 5 base 10. Now we are going to add these two numbers. Okay, so say this table, my binary addition of minus 21 and 5. So minus 21 base 10, what is the binary value? 111010111. And then 5 base 10, what is the binary value for this? 5 zeros 101. Okay, now we are going to add these two numbers. So 1 plus 1, what we get? We already studied, in binary addition table, 1 plus 1 is equal to 1 0. How we can get the value 1 0? 1 plus 1 we get 2. 2 is not a binary number, so we convert 2 into the binary format. 2 divided by 2, the quotient is 1 and the remainder is 0. Okay, so you put 0 in the sum bit and 1 is a carry bit. Okay, so 1 plus 1 it equal to 1 0. So 0 and then 1 is carry bit. Again we see the next bit, 1 plus 1, again we get 1 plus 1, again we get the answer 1 0. 1 0 plus 0, we get the same answer 1 0. So you put 0 in the sum bit, again 1 in the carry bit. Now we can add 1 plus 0 1, again 1 plus 1 we get 1 0. So you put 0 in the sum bit, again 1 is a carry bit. Now we can add 1 plus 1, again we get the answer 1 0. So you put 1 0, again 1 0 plus 0, we get the same answer 1 0. Okay, so 0 is the sum bit and 1 again is the carry bit. Now we can add 1 plus 0, what we get? 1, again 1 plus 0 we get 1, so you put 1 in the sum bit. And the next bit, 1 plus 0 1, 1 plus 0 1, 1 plus 0 1. Now this is a result. This is equivalent for minus 16 base 10, decimal number minus 16 base 10. Okay, is it clear? Minus 21 plus 5, what is the answer we get? Minus 16. The minus 16 equivalent binary number is 410000. So this is the answer for this question. Okay, is it clear? Now you can understand how to do the binary addition for negative number and positive number. Okay, so if there is any negative number, then you can go for 2's complement method to find the binary value, and then we just add the normal procedure for binary addition table. Okay, Is it clear? Okay, students. Now we move for the next topic, representing characters in memory. So now we see about how to represent a characters in memory. What is mean by character first? We already know, no? Characters are the individual digit. It may be the alphabetical letters or numeric numbers or any other special characters. Okay. So this also known as character set. What are the characters is needed to write a program is collectively known as a character set. Okay. So in general, 26 uppercase letters. In alphabets, how many uppercase letters are? A to Z. 26 uppercase letters. We also having 26 lowercase letters. And then numbers are 0 to 9 digits are available. Okay. And special characters. What are the special characters? Comma, semicolon, full stop, and then division, addition, subtraction, multiplication, the symbols. Okay, all the symbols is considered as a special characters, are used in a computer, which is called a character set. So these are all known as a character set. Now you can see how these characters are represented in a computer memory, how the computer can respond each and every characters also. Okay, all these characters are denoted through numbers only. We already learned, computers can understand only the binary language. Whatever we are feeding input to the computer, that is we are giving text data, audio data, graphics data, numerical data, the computer can understand only the binary format. This data are converted into the binary form. So how this conversions can be take place, how the common encoding systems are found. Now you can see that one. Okay, all characters in the character set needs a common encoding systems. So encoding means we are changing the input data format. Okay, the encoding systems are, there are several encoding systems are used in the computers. Okay, now we are going to discuss about 5 encoding systems given in your book. BCD, binary coded decimal format, and then ABCDIC, extended binary coded decimal interchange code, ASCII, American Standard Code for Information Interchange, and then Unicode, that is Universal Coding System, ISCII, Indian Standard Code for Information Interchange. So these are the different encoding system used in your computers. Here BCD is the oldest format. Okay, nowadays we are not using this binary coded decimal format because BCD code is using only 6-bit code. For that we can able to represent only 64 characters. So this is used in the old versions of computers. Now we are not using this BCD code. Now you can see one by one in detail. Okay. So binary coded decimal format. This encoding system is not in the practice right now. Okay, now we are not using this encoding system. So this is 2 power 6 bit encoding system, 6-bit characters. Okay, so totally how many characters we can able to represent? 2 power 6 equal to 64 characters only you can able to represent in the computers. Okay, so in 1 mark questions, they will ask like this, how many characters can be represented in binary coded decimal format. Okay, so you must remember each and every encoding system, how many bits are possible to represent and how many total number of characters you can able to represent. Okay, in binary coded decimal format, how many bits you can able to represent? 6-bit encoding system, 2 power 6 bit encoding system, and you can able to represent only 64 characters. Okay, and the next coding system is American Standard Code for Information Interchange, ASCII code. 11th standard also we studied, no, ASCII code. Okay, now you can see that one. So this is the most popular encoding system. So ASCII code is the most popular encoding system recognized by United States. So most of the computers use this system. So the standard code was developed by United States. Okay, so remember this encoding system can handle English characters only. Okay, so American Standard Code is used to handle only the English characters. Okay, so there are two versions of ASCII codes are available. One is 7-bit code, another one is 8-bit code. Okay, this can handle 2 power 7 bit, which means 128 characters. In this system, each character has individual number. Okay, 128 characters. Each character has the individual number. Okay, the new edition ASCII encoding system new edition is ASCII 8. That is 8 bits code. Okay, 2 power 8 bits code, and can handle to 56 characters. How we can say 2 power 7 is equal to 128? We just multiply the numbers 2 into 2 into 2 into 2 into 2. Why? The base is 2. In binary number we are having only two possible values, that is 0 and 1. So we are using the base value is 2. Okay, so and depending upon the characters we can put the power. 6-bit character means we put 6, 7-bit means we put 2 power 7. Okay, so ASCII new edition is ASCII 8, that is 2 power 8 bits and can handle 256 characters, are represented from 0 to 255. That is the first number digit is 0 to 255 unique numbers. For example, if you want to represent 0 in ASCII 8-bit code, how we can represent? 8 zeros are used to represent a number 0. If you want to represent 1 means 7 zeros and 1. Okay, so this is the ASCII value for numeric number 1. For the same way, we can represent each and every character in ASCII. Okay, so here also one example is given. See that one, the ASCII code equivalent to the uppercase letter A. So uppercase letter ASCII value is 65. How we can represent in binary numbers? In 7-bit value, we can represent 1000001. So this is the ASCII value for 7-bit value. The same number, that is the same letter uppercase A, will be represented in 8-bit means we are using 8 bits. So bit is nothing but either 0 or 1 is known as a bit. Okay, binary digit, the expansion of bit is binary digit. So binary digit means either 0 or 1. 8-bit means totally we are having 8 digits. Okay, so now you can see how the capital letter A is represented in 8-bit format. 0 1 0 0 0 0 0 0 1 in ASCII 8-bit values. Okay, so here we are taking the example capital A. The capital A equivalent ASCII value is 65. So how the 65 is represented in binary format? We already know how we can convert a decimal number into binary number. Okay, so the equivalent binary value for 7-bit is 1501 and then 8-bit is 01501. We just increase one more bit in 8-bit representation. Okay, so now you can see about extended binary coded decimal interchange code, that is EBCDIC code. This is similar to the ASCII code with 8-bit representation. Okay, so EBCDIC code is also the 8-bit representation. This encoding system is formulated by International Business Mission, that is IBM. ASCII code was formulated by United States. Okay, so here EBCDIC code is formulated by IBM. What is the expansion of IBM? International Business Mission. Okay, what is the expansion? International Business Mission. The coding system can handle 256 characters. So 2 power 8 is equal to 256 characters. The input code in ASCII can be converted to EBCDIC system and vice versa. We can able to convert ASCII code into EBCDIC code as well as EBCDIC code into ASCII codes. Okay, we can use both the codes interchangeably. Okay. So next one is Indian Standard Code for Information Interchange, ISCII code. So it's the system of handling the characters of Indian local languages. Okay, so this ISCII code is used to represent a characters in Indian local languages. This as a 8-bit coding system. Therefore, it can handle 256. We already discussed two 8-bit encoding system. No, what are the two 8-bit encoding systems? One is ASCII, another one is EBC DIC code. Okay. Now one more is Indian Standard Code for Information Interchange. So these are all comes under the 8-bit encoding system. Okay. So how many characters you can able to handle? 256 characters you can able to handle this three encoding systems. Okay. This system is formulated by the Department of Electronics in India in the year 1986 to 88 and recognized by Bureau of Indian Standards BIS. Okay. So this system was developed by Department of Electronics in the year 1986 to 88 and then recognized by Bureau of Indian Standards, that is BIS. So now this encoding system is integrated with Unicode. That is now next we study about what is mean by Unicode. Okay, this ISCII coding system is integrated, that is merged to the Unicode encoding systems. Okay. Unicode, that is Universal Code for Indian Local Languages. This coding system is used in most of the modern computers. And that is, if the number of bits is increased, means you can able to represent more number of characters. Okay, so ASCII also there are two versions, no, ASCII 7-bit code, ASCII 8-bit code. Now you can see Unicode is a 16-bit character, 16-bit encoding system. We can able to represent 2 power 16 characters. Okay, so this encoding system is used in most of the modern computers. The popular coding scheme after ASCII is Unicode. Okay, there are several encoding systems are available, but most popular encoding scheme is first one is ASCII. After ASCII is Unicode system. ASCII can represent only 256 characters, and then ASCII uses only the language English and European languages. Okay, so particularly there was a situation when the language like Tamil, Malayalam, Kannada and Telugu could not be represented by ASCII. Why it is not represented by ASCII? Totally how many characters in Tamil? In Tamil and Malayalam, Kannada, they are having too much of this, 200 and something characters is there. Okay, in English we are using only 26 characters. So 26 characters can able to represent in ASCII code. But this local languages, Indian local languages, Tamil, Malayalam, Kannadam and Telugu, we can't able to represent in ASCII code. For that we are developing the new encoding system, that is Unicode. The Unicode was generated to handle all the coding system of universal languages. Okay, so universal languages can be represented by the Unicode. This is a 16-bit coding system and can handle 65,536 characters. Okay, how many characters can able to handle? 65,536 characters you can able to handle. Unicode scheme is denoted by hexadecimal numbers. We already studied, no, what are the different types of number systems are used. So Unicode scheme is denoted by the hexadecimal number system. ASCII codes are denoted by binary number system. Okay, Unicode scheme is denoted by the hexadecimal number system. So now you can see one table is given in your book. Alphabets, letters, equivalent decimal number, binary number and octal number and hexadecimal number systems. Okay, alphabetic letters A, the equivalent decimal number is 65. So how we can represent in binary number? Either we can use sum of powers of 2 method, or we can use repeated division by 2. So 65 equivalent 8-bit number is 01501. Okay, octal number. How we can convert 65? How we can convert decimal to octal? Repeated division by 8. 65 divided by 8. 8 8s are 64. Remainder is 1. Again we divide by 8. 10. Okay, so we write the answer 101. So 65 divided by 8. So 8 8s are 64, remainder is 1. Again we divide this by 8. So 8, so 1 8s are 8, remainder 0. 1 0 1. So this is the actual number for 65. Okay, and then hexadecimal number. So 65 divided by 16. 4 16s are 64, remainder is 1. So we get the answer 4 1. Okay, we already discussed how we can convert decimal number into binary, octal and hexadecimal. You can use repeated division by 2 for binary number, repeated division by 8 for octal number, repeated division by 16 for hexadecimal number. We can find the value for each and every numbers. Okay, for this alphabetical numbers is already defined to the computer. Okay, so no need to convert yourself to store in the computer. We just understand how these numbers are converted and stored into the computers. For that only this table is given. Okay, is it clear, ma? So alphabetical numbers and numeric numbers also given the table, and then special symbols also given. So we just go through all these tables. Okay, okay students, that's all about chapter 2 first part. In the next video we see the chapter 2 second part, that is Boolean algebra. Okay students, thank you.